Right. Hello, everyone. Welcome to our next lecture on quantum computing. And today we will be discussing two-qubit operations and the last uh, part of our recipe for quantum computation, which is called entanglement. All right. So today we will learn how we create entanglement state of several qubits. Yeah, as usual, I'm starting with importing some libraries, and let us quickly overview of what we learned, right? So all this is based on computational unit, which is a qubit, right? Is a system that can be in two states simultaneously at the same time. These two states are uh, basis states, right? In the case of a qubit, it is zero state and state one, multiply by this alpha and beta, which describe the probability or probability amplitude of finding this state or this state in the experiment. Okay, so you have a qubit, you measure it. This qubit can be in the zero state or state one, and with different probability, which you can control and prepare, um, you get zero or one. So it's random, right? You cannot predict, you cannot say in advance the result you will get. The only probability what you have here. To represent a state of a qubit, since it is not only uh, 0, 1, it's also phase there. This alpha and beta encode phase, and this phase corresponds to different orientation of this state vector psi in the Hilbert space. So we can represent any quantum state of a single qubit using the block sphere, and this is the way we do so. We attribute this theta and phi in this Hilbert space that indicates the direction of the quantum state. We discussed the quantum gates with the focus on single qubit quantum gates, right? The most important quantum single qubit quantum gates are uh, Pauli gates, uh, Pauli gates, Pauli gates, X, Y, and Z, which essentially rotate this state vector around X, around Y, and around Z. Okay. And the Hadamard gate, indicated by H, it's an important type of gate because it creates superposition. Initially, our qubit in the state 0, which is dictated by the fact that any system tend to the ground state as it evolves. So our qubit in 0 state, and then we apply this Hadamard, and the Hadamard gate creates the superposition of two, the balance superposition with equal probability amplitude 1 over square root of 2. Okay, and we also discussed some preliminary like elements, basics of using Qiskit for quantum simulations. Basically, we were able to discuss only state vector simulation, right? As far as I remember. So state vector simulation. But let me kind of here I try to structurize all these steps you make to run the simulation using Qiskit. So usually you start from importing necessary packages, right? These packages include these functions or commands that allow you to create a quantum circuit, right? Quantum and classical registers. Quantum circuit consists of quantum register and classical register. Qiskit Air we will be discussing today. Qiskit Air is one type of Qiskit solver that allows you to mimic the functionality of a quantum computer. Okay, so like broadly speaking, Qiskit allows you to do three different things. One is the simplest one. You can run simulation on your local computer, on your local desktop. Second, you can send your project to IBM's backend. It allows also to run simulation somewhere else, provided that you have a quantum computer available. Okay, but usually it's IBM quantum computer. Backend. So Air backend means you mimic functionality of a quantum computer. It's not real quantum computer, but this solver provides some noise, inaccuracy, and so on that generates the result, like simulation, very close to what would you get if you run it on a quantum computer. Okay, and the third type of simulation is the truly quantum computer simulation. When you send your project to a IBM real quantum computer, it's they have just a number of them, okay, available, and just a few available for us for educational purpose. Right. So usually it's like a line there. Today it was pretty nice. I was able to run some circuits, like maybe 2 or 3, and the waiting line time was maybe 15 minutes or so. But usually it's a little longer. All right, so you import the libraries first. Second, you create a quantum circuit, right? You start with, you can start with the creation of quantum register and classical register, but that's not kind of required. You can simply create a circuit or announce the circuit using this command quantum circuit. Okay, the quantum circuit consists of the quantum register. For now, here I put 3, so it's a 3 qubits in the system, and the classical register with 3 bits, right? In the classical part of the circuit. All right, then you build your quantum circuit. So far we discussed only single qubit operations. So let me add these 3 gates in there. Hadamard X and Y apply to the first, second, and third qubit in this circuit, right? And then also I put this barrier, so it doesn't do anything. It's just graphical line. Let us do without it first. Yeah, I need to run this one. Yeah, and then I can visualize my my circuit, right? So this is the circuit now. 3 qubits, H X and Y, gates applied. And this double line always means classical bus line. Yeah, regarding this barrier, I can do this. I can put this barrier to the circuit just to separate the parts of my circuit. Okay, so like after barrier, I can add something else, and these two parts of the circuit will be separated. Okay. Yeah, and then you need to simulate your circuit, right? And to do so, you have several options available. Qiskit includes many types of solvers, and we will be looking into just 2 or 3 of them, but there are much more available for people who work in this area, including some machine learning, quantum algorithms, and so on. Today, people look more and more into machine learning aspects of this technology, and many people, including myself, I believe that machine learning will develop this. I mean, the future is for the machine learning approaches, because machine learning allows you to do something useful, having a system with just a manageable or feasible number of qubits. Okay. Say for useful quantum computations today, we would need quantum computers with 1,000,000 qubits. But so far, the state of the art is maybe 1,000 qubits. Okay. At the same time, using just 1,000 qubits, you can do some non-trivial machine learning stuff, quantum machine learning stuff. So for near future, machine learning will be playing a big role here. What I was talking about. Yes, so the first simulator is the simplest one, just state vector simulation. It is nothing but just this is the circuit, this is your input, this is the output state in a perfect case. So no noise, no loss, just perfect simulation. It's not a simulation, actually. It's just the multiplication of matrices that represent the gates, right? So to do so, I run this. So what I did, so I have this circuit here, okay, with qubits 0, 1, and 2. I indicated my starting or initial state input is a state vector 0. 0 here means state 0, 0, 0. So all qubits are in the 0 basis state. Okay. And then I asked to evolve this state dot evolve, and I apply this to the circuit. This is the name of my circuit announced here. Circuit. State change it so now it's in. Okay, so this is the output. Let us look at this. Let us look at this output. So the input state 0 means 0, 0, 0. Okay, so 0, 0, 0 states in the input, and in the output we've got this superposition of two state 1, 1, 0 and 1, 1, 1. Okay. So what is important about this state is the fact that this state is separable. Separable. It means that you can separate it. Okay, separate. Look at these two units, and one here and 0 here. So you can write this state as a product of three states of qubits. Okay, so it's a separable state. It's not entangled state. And this is important because for quantum computing, we need another type of state, which is non-separable state or unseparable state, also known as entangled state. Okay. So from this point, what is important to kind of take home is the fact that you cannot create entangled state using only single qubit gates, because single qubit gate applies to different qubits, and they are they stay not entangled. Okay, so next type of a simulator is called Ayer-Casem simulator. So this Ayer-Casem simulator is exactly what I discussed. This simulator emulate the behavior of a quantum computer. So it's not a real quantum computer, but it emulates that. Okay. What is the limitation of this simulator? The limitation is simply the number of qubits that you can simulate on your machine. Typically, it is something around 30, maybe for a good desktop computer, 50 for a supercomputer, and this type of simulator is not applicable to a system with, let's say, 100 qubits, because the system becomes so complex, and you will need to use another type of simulator. So for to be able to use this custom simulator, you need to import Ayer from Qiskit Ayer. And then I already have my circuit, this one, 3-qubit circuit. I need to supply my circuit with the measurement part, okay? Because any quantum computing simulation must end by measurement of your circuit, of your qubits. So we need to add this measurement gates, okay, which are the only not unitary gates in this in this area. Okay, so they are not time reversible. These measurement gates, they measure the qubits in their states, and the result is random. It's with some probability, right? So this is my circuit that I plan to simulate using custom simulator. The procedure is similar. So I'm starting with the announcement or creation of the simulator, and I say what is my backend. So my backend is custom simulator, because custom simulator is only one possible type of simulator in this AIR package. AIR includes much more. These simulators, they are different in terms of what is the model for the noise, what type of noise it includes, and so on and so forth. Also, there are some different approaches to simulate. AIR simulator, AIR package includes this simulator based on density matrix approach. We didn't discuss that, but yeah, so much more is there. Custom is just one example. Okay, and then we create a job, right? So it's our project. I take my simulator and ask it to run. Okay, so it used to be execute maybe a couple of years ago. This approach was kind of a little bit different. It was AIR without this Qiskit AIR, without this underline AIR, and then instead of run, it was execute and some other differences. So make sure that you use the updated approach, right? With run in here. So simulator, then run, and then name of your circuit and the number of shots, right? The number of experiments you conduct, you measure the result of your simulation. Okay, then you need to retrieve the result with name of your job, right? It's just job dot and this method dot result. So this is the result. Then there are different ways to represent your result, right? Histogram, block sphere, Q sphere, maybe some CT diagrams, vectoral, and so on and so forth. So we use we extract counts, and for counts we plot. Oh, before that, we just here we return only the number of counts. So now, so we see the result. It is out of 1,000 shots. Let me change this number to 1,000. So out of 1,000 runs, it returns me state 111 493 times and 110 507, right? If I run it again, these numbers are a little bit different. Again, still different. So it's a random, but as you grow the number of shots, it is this randomness kind of go away, and you get the very well-defined result, which consists in the fact that these two states appear with very, very close probability. Okay, so their probability amplitudes are the same, which means that for this circuit, the perfect simulation gives us this, right? So this amplitude and this amplitude here. So this is the perfect simulation. This is the simulation with some noise taken into account. We can represent this data using histograms. This is the result. Again, if I run it, it changes a little bit. If, for example, I run my experiment just 10 times, right, the difference between these two histograms is much greater, right? It's noticeable. Again, if I run another experiment 10 times, again, so you cannot say that these two states they have the same probability. The smaller number of experiment doesn't produce the result. However, if you increase the number of shots, you see that these states are symmetric or have the same probability amplitude. And finally, real quantum computer simulations. Okay, so AIR is for emulating quantum simulations. Now we need to use Qiskit IBM runtime package to run the real quantum simulations on a real quantum computer. So we install this one as usual, pip install and the name of the package, right? And after you install it, you can import this from Qiskit IBM runtime, import Qiskit runtime service. Okay. This function allow you to basically connect your project in here in Jupyter Notebook to your account in IBM Quantum. So this is my account in IBM Quantum, right? I believe you all already registered in here and got your personal IP token. Okay, you will need this IP token for your homework and your lab work simulations. Okay, so this IP token is a kind of a number. I can refresh it. Yeah, I can regenerate it to get a new one, and then copy, and then in a line like this service name of the function, the channel IBM Quantum channel can be different if you use Google Quantum Computer, right? It will be something else. For now, we use IBM Quantum, and then for this token, I copy and paste the new one. Okay, and then execute the cell, and hopefully it will get it. Yes. So now I'm using this token from my IBM Quantum platform. All right. Then the backend. Okay. So if you go to IBM Quantum platform and then to the compute resources. By the way, do you see my screen, right? I don't see this green frame around.
Yes.
Yes.
Okay. Okay. So compute resources. You will see kind of different different computers, different backends here. So let me see. So all of these are quantum computers. All of these are quantum computers with the number of qubits indicated here. So this one, for example, gets 156. This one is 133. So just recently, they also had computers with number of qubits just maybe like 10 or 6 for education. So now it seems like they use only this computers with number of qubits higher than 100. Anyway, so these are available, which is indicated by this green online status, right? So it's this, some of them available to you, but not all of them. Okay. In order to check what backends, what computers available for your simulations, you run these backends, then service backends to download this list of backends, and then you can return the list of them. For backend, in backends, you print the name, right? So hopefully it will return the list of, yeah. So you see it's just free. So only free from these, how many, like 10 available to you for this calculations. Let us see. IBM Brisbane is this one, 127 qubits. Another one is IBM QIF. This one, pretty much the same. And Sherbrooke. Sherbrooke is this one. Yeah, so they are pretty much the same. If you click on the particular backend, you will see kind of more information about this computer. So first of all, this is the computer topology. Okay, so each circle here indicates the qubit. Okay, so you see that the qubits kind of connected in this chain, right? Some of them connected with 3 neighbors, others connected with 2 neighbors. There are some qubits that connected with just 1 neighbor. Different qubits also indicated by different color. Okay, different color means readout error. Okay, so it's basically the quality of the qubit. The darker this color, the better the qubit. So you see, even though the system was fabricated using the state-of-the-art facility of IBM company, still there are some qubits that behave relatively worse than others. Okay. For that reason, before running the circuit, there is operation is called transpile. Okay, for any particular computer, transpile operation kind of changes it in order to be run most effectively on a particular computer. Okay, because if you go to another one, what was IBM Q, for example, right? Isn't it this the same? No, it's different. Yeah, so you see, it's also, I mean, the topology is the same, but the qubits different. Yeah, the qubits different because of the fabrication issues in accuracy. Okay, so for our purpose, we can use any one. Let us do the first one, IBM Brisbane. Yeah, I already did it. So I run it, and yeah, I connected to my, or chosen to my backend. So then I do this transpile operation of my circuit. So transpile, again, it prepares the circuit to be executed on the particular machine. Okay, I do transpile. It takes some time, yeah, and then I can draw what I got. Okay, so my circuit that I am after, I plan to simulate is this one. So it's a theoretical circuit, just a circuit of consisting of 3 qubits with a single qubit gates, Hadamard X and Y. But after transpiling this circuit, I got this. So this is exactly the same circuit, but kind of uh, encoded, right, into the computer with 126, 27 qubits, and also gates, right? Instead of Hadamard, it is represented by this the product of 3, for example, and so on. So it's a it is exactly the same circuit, but prepared to be executed on a particular quantum computer. Okay. Uh, yeah, I commented these parts here because if I run it, it will send the project to IBM Quantum, and then I won't be able to use the rest of the code. We can send it together. Like now, I have I have no projects in line, so I can send this one. Okay, so job, then backend, get run, then transpiled circuit, number of experiments, and then you get results from the executed project, and the format of the result is counts. Okay, so now it's thinking if I go to my system, and I guess if I reload this page, I will, yes, I get this project here, sent to IBM Brisbane, right? If I go to this particular project, I will see my circuit in here, right? Transpile circuit. Also, status pending, timeline. When it's created, pending, then in progress, and completed. Yeah, so now this project is in line, and when it's done, I can visualize the results using this histogram. The result will be very similar to this one, because uh, because AR simulator is very good in emulating a quantum computer, basically. Right. So let me restart and your output and comment this and these lines. Okay. So in your homework, you will be asked to do this simulation, getting results and visualization for your particular circuit. So in your case, it will be something something else. Now I need to run this cells again. Yeah. Yeah. So again, this is our current circuit. In your homework, you will be asked to simulate some other circuits. Okay, but the procedure is essentially the same. You will be asked to use two types of simulation. One is classical, which means custom simulator. So you apply this approach in the point in the chapter 2.52. This is the first part. Then for the real quantum computer simulation, you use this part 2.5.3. Okay. Do you have any questions about this part? Okay. So if not, then let us continue and discuss two-qubit gates. So very important part, right? Two-qubit gates are applied to two qubits, right? So simple. They apply to two qubits, and it means that the result of their operation is depends on the state of two qubits. Instead of one qubit as it was for single qubit gates, now the result depends on the state of two qubits. Okay. The most important gate is CNOT gate, also known as control not gate. This C stands for control, or CX. Okay, CX, CNOT gate. This is the schematic presentation, right? So it is a bold circle connected to the upper qubit, and this second qubit, it is a this white circle with the plus inside. So you remember this plus circle with the plus means X gate or Pauli gate, Pauli X gate. So this notation means my Pauli gate, Pauli X gate is applied to the second qubit, but its operation depends on the control qubit, which is upper qubit. So this bold means control, and the second one is target qubit, control and target. In terms of the matrix representation, this is the matrix. So it's a 4x4 matrix because now I'm working with two qubits, right? Two states, two states of one qubit, two states of another qubit. Multiplication creates the state with four terms. So input is 4 and output is also 4. So the matrix is 4x4. Right, so applying this CNOT gate to the basis vectors. So now I have 4 basis vectors, 0, 0, 0, 1, 1, 0, 1, 1. Which basically enumerate all possible states of the first qubit and the second qubit. This is the first, this is the second. So let us see. Let us see for this particular case. This is classical notation, okay? And in classical notation, the first qubit, the leftmost, is the control, and the second is target, okay? So I apply my CNOT to this one. I see that my control is 0, then my target is 0, 2, so it doesn't change. If it's 0 but target is 1, it's also 1 in the output, doesn't change. However, if my control is 1, then my target changes the state. from 0 to 1 or from 1 to 0. So it's so simple. So simple. Let us show the CNOT gate, how it's used in Qiskit. This is the presentation, right? In IBM Quantum, if you go to in here, Quantum Composer, right, you will find this you will find this qubits. Sorry, gates. What's going? Maybe because of the simulation. All right. Anyway, so this is the representation. Again, control and target. Let us check how it works in state simulation, right? So it's a state vector simulation. I call for state vector simulation approach. This is the initial state 0, 0. And then for my circuit, which is this one, I have state 0, 0 in input, and my output is 0, 0. However, if I change, for example, this one to 1, I get 1, 1. So you see that, and if this one gonna be 1, then it's gonna be, the result will be 0, 1, right? The result's gonna be 0, 1. So you see that in Qiskit, this notation is a little bit different. So if in classical textbooks, control is the leftmost, in Qiskit, control is the rightmost. Okay, and as you add more qubits to your system, usually it runs from left to right, right? So this is my first qubit, second qubit, third qubit, fourth qubit, and so on. But in Qiskit it is from right to left. So it's my first qubit, then my second, third, fourth, and so on. So it's from right to left. This is kind of difference that used to remember of, and I took this note from their website. Okay, discussing this fact, and as a result, the actual matrix for the CNOT operation is not this one, but this one. Okay, so it's a little bit different. A little bit different. So next 2-qubit gate, important 2-qubit gate is Control Z gate. We will meet this one when we will be talking about some quantum algorithms. Okay, Control Z. The principle is the same. It's just if my probe is 0, then this qubit, this gate doesn't do anything. But if it's 1, then it applies the gate, right? This Z gate, for example, here. So Z gate is what? Is flip of phase, right? And this is the algebra. This is the truth table, right? If it's 0, then the result is 0. Then when it's 0, the 1 is still 1. But if it's 1, then for the 0 it doesn't change phase. But if it's 1, it changes phase of the target qubit. Changes phase by pi/2. So simple. yeah, similarly, we can run this using state vector simulation for the Control Z gate, right? This is CZ, so Control Z gate, and for the 0, 0 state, we got 0, 0, and so on. But if I do 1, 1, it will be minus 1, 1. So finally, this brings us to the concept of entanglement. Okay, so entanglement is a phenomenon where the state of one qubit is dependent on the state of another qubit, no matter the distance between them. So consider this as a matter of experimental fact, experimental reality. I don't understand how it works, and no one in the world can explain how it works. But this is the matter of fact, right? So suppose you have two qubits, they can be in 0 and 1 state in the same time, right? Then you bring them to interaction, and this is they interact and they mixed up with their states, which means that um, the the um, the state of one affects the state of another one. Okay, but this is something, we can see this in classical physics. If you have one resonator, another resonator, you bring them together, of course they interact, and if you change one's resonator, it will change another one. But the key point here is that if you take these two qubits apart, they still will be entangled. So you take them, interact, take them apart, and they will be entangled. Which means that if you measure the state of one qubit, it will immediately, at the same time, like instantly, affects the state of the second one. So the most entangled state is so-called Bell state. There are four different Bell states. They are listed here. So you see that Bell state is a state in which the system of two qubits either in the state 0, 0, okay, or state 1, 1 with the same probability. Okay, so let us consider this state here. So two qubits, one can be in state 0, state 1, another one in state 0, state 1. They interacted, you make them apart, and now they are in the Bell state. Okay, so what happens is, suppose you measure one of the qubits. Okay, what can be the result? Either 0 or 1. So let's suppose you got 0, right? Then you immediately see that this Bell state collapses to this one term here, because no 0 for the second qubit in here. So it's only one term with 0 state for this qubit in this term here. So 0, 0, which means that the second qubit also collapses to the state 0, and you end in this state 0, 0. However, with the same probability, you could find state 1 in this experiment. Then immediately you conclude that the second one is also in the state 1. And since this is how the nature works, since we have to take these two states into account like simultaneously, it's not like oscillation. It's not only one state. It's like simultaneously uh, present two states the same time. It means that when we measure one qubit, we kind of uh, collapse our world to in which the second qubit also gets the same direction, the same state. This is very kind of puzzling and interesting, but people demonstrate this in experiment, and this is behind all quantum simulations, so it is probably the truth. The point here is also no matter the distance. So if you take one qubit to the moon, for example, and do that measurement in there, you will make the second qubit, which is on the Earth, collapse to the either state, 0 or 1. Very interesting. Similarly, there is another state which depends on the previous one by sign, which is phase, right? And other two states which 0, 1 and 1, 0. So you see these states are not separable. You cannot present this state as a product of two states of an individual qubit. Very drastically to what we saw in here, for example, right? So in this state, give me a second, I need to. What was I? Yeah, so this state, you see here, this state, look at this one, for example, one here and here. So you can represent this state as a product of one and 1, 0, 1, 1, 1, right? So it's a separable state. It's not a entangled state. The Bell state is a non-separable and entangled. Non-separable and entangled. So how we create entangled state? Let us, for example, consider this particular case. So let us start from the state 0, okay, of a first qubit, and apply Hadamard gate to this first qubit. And the result is the balanced superposition of two states, state 0 and state 1, with equal probability. All right, so this is the state here. And then I apply a C0 gate with control connected to my first qubit, which is this one, in superposition. And the second, the target is a second qubit, initially in state 0. Do I have a circuit here? It's supposed to be this one, right? Give me a second. This one. Yeah. So this is the part I'm talking about. You apply Hadamard to the first qubit. Hadamard creates superposition of two states with equal probability. 0 state does not affect the second qubit, but the state 1 affects. It flips the state of the second qubit. In quantum, we consider these two options at the same time because they happen at the same time. So this second qubit, you don't know in what state it will be after this circuit, because it will depend on the state of the first one, of the first qubit. So these two will be entangled. So you apply the C naught to this combination in here. 0 will leave it unchanged, the second one. The state 1 will flip it to the state 1. So this is the result of this circuit. Yeah, a few words about measurements and properties. So first of all, measurement outcomes are correlated regardless of distance. That's what I try to say by sending one of the qubits to the moon. Yeah, so measuring one qubit immediately affects the state of the other one. It's not correct to say state. It does not affect the state, because that state is already there, but we have these two states at the same time. So we don't affect one of the states. We just select one of the possible states existing there simultaneously by measuring other qubits sent to the moon. Okay, so there is no kind of connection between them. Nothing travels with the speed of light, for example. So you cannot transfer information, for example, making these measurements. So it doesn't break the Einstein's theory, no relativity. Okay, so we create Bell states using a circuit which is called golden two-qubit quantum circuit. Okay. So what is golden two-qubit circuit? Is this one, right? The Hadamard and the C naught gate. Hadamard and C naught gate. In the input state is 0, 0. The output is the Bell state. Of course, one can generalize this approach to a system of more qubits. And for example, for a system of 3 qubits, in order to generate this entangled or perfectly entangled state, you can use such a circuit here. So you see, you still generate superposition of the first qubit, then this superposition creates the first entanglement with the second qubit, and then that entanglement creates another kind of entanglement of the third order with the next qubit. And if you put more and more these C naught gates, you will create more and more complex state. So this is the perfectly entangled state of 3 qubits. Again, if you measure either one, let's say we measure second one, this Q1 in here, if we get state 0, then we immediately conclude that our first and third qubits are in the state 1, so in the state 0. But if we found second qubit in the state 1, we immediately know that the other two qubits are in the state 1 too. Okay. Again, these two states live there simultaneously at the same time, and by measuring the qubit, um, we just um, find out, how to say, it's like two clones of the same system living present, and measuring one of the qubits collapses these two clones to one single possibility, one single system. Yeah, again, it's pretty tricky because we don't observe these effects in our classical world, but this is how quantum world behaves. Entangled state. This entanglement, by the way, is behind a lot of applications today. For example, this um, quantum cryptography, right, or quantum this key distribution approaches. Some of them rely on this entanglement principles. All right, so let us discuss finally how to simulate a real, this two-qubit golden circuit using a real quantum computer. Right, to do so, again, we choose the backend, right, backend. Then we draw our circuit, we create the circuit, then we apply Hadamard to the first one, and then Control X with first one being control and second being target, right? And then we measure all qubits in our circuit, right? So this is the resulting circuit to be sent to the quantum computer. Then we need to transpile this circuit, right, by using this transpile function. Take some time. Yeah, this is the result. Okay, so you see now, in contrast to the first project we sent to the quantum IBM here, right? These qubits, these lines, they are not connected along the line. No connection between the qubits. Now in our current circuit, there is an element that connects the two qubits, which means that these two qubits are entangled. Before measurement, they are entangled. Again, this transpiled circuit is exactly the same as this one. Qiskit just creates a transpiled version to make it more feasible and solvable using particular quantum machine. Right, and then you need to send this project to the IBM backend, right? And then when it will be executed in a while, so it's sent, we can check what that project appeared in my project list. Oh yeah, it was frozen. So it got stuck. I don't know. Okay. So let us see that I have that project on my project list. Okay, yeah. So this project appeared on my project list, and here It will be executed in a while, and when it will be done, I will run to get my results and present them using the histogram and so on. Of course, like in my case, I have like many projects executed, right? Of course, I can retrieve the data from those projects, and this is the piece of code how to do so, right? You need this job ID name, which is this guy here. This long number is the project ID, and then you basically can get your results from your account. All right, so let me save this and stop recording, then we can discuss.